that gravity is real?
Gravity is something you never escape. Every second of every day it holds you against the ground, keeps air wrapped around our planet, maintains Earth on its orbital path around the Sun, and orchestrates the movements of galaxy clusters separated by incomprehensible distances. Yet what most people believe about gravity turns out to be only half the story. The deeper truth is that gravity is not really a force at all. It is something far more peculiar and far more elegant. Most of us grew up learning a straightforward picture. You release an object and it drops. Earth pulls everything toward its center. The sun pulls Earth. The moon pulls the oceans. All of that is serviceable for everyday life. But it resembles calling our planet flat, because the ground looks level from where you stand. It works locally, but it conceals a grander reality. Back in 1687, Isaac Newton laid out the mathematics governing gravitational attraction in his landmark work, commonly known as the Principia. Before Newton, explanations for why objects fell or why celestial bodies moved were mostly speculation. Newton demonstrated that the mechanism making an apple tumble from a branch is the very same mechanism holding the moon in orbit and keeping our world circling the sun. That was a radical unification because people had long assumed that earthly and heavenly motions obeyed entirely separate rules. Newton's universal law of gravitation says every massive object attracts every other massive object. The strength of that attraction grows with the product of their masses and weakens with the square of the distance separating them. You and Earth tug on each other strongly because Earth is enormously massive. You and a coffee cup across the room also attract each other, but the pull is so vanishingly faint that no human sense could ever register it. To put that faintness in perspective, two people standing a meter apart attract each other gravitationally with less force than the weight of a single bacterium. Gravity is roughly 39 orders of magnitude feebler than electromagnetism on everyday scales, which remains one of the deepest unexplained puzzles in all of physics. And because of the inverse square relationship, doubling the distance between two objects does not merely halve the pull, it drops to 1/4. Triple, the separation and the attraction falls to 1/9. That scaling is why gravity only dominates when truly colossal masses are involved. Newton's framework was spectacularly successful for more than 2 centuries. It predicted planetary trajectories, explained ocean tides, clarified why distant planets orbit more slowly, and even enabled the discovery of Neptune in 1846 when astronomers noticed that Uranus deviated slightly from its predicted path, calculated where an unseen world would need to be to cause that deviation, aimed their telescopes, and found the planet exactly where the mathematics indicated. Still, tiny discrepancies lurked. The most stubborn involved Mercury. Mercury traces an elliptical orbit that gradually rotates over time, a phenomenon called precession. Newtonian gravity accounted for most of that rotation through the gravitational influence of other planets. But observations showed an extra shift of about 43 arcseconds per century, roughly 1/50th of a degree every 100 years. Minuscule, yet persistent and reproducible. Researchers hunted for explanations. Some proposed a hidden inner planet they called Vulcan. It was never found. Others tried tweaking Newton's equations. Nothing resolved the puzzle. It lingered for decades until a patent clerk turned professor named Albert Einstein offered a completely new framework. In 1915, Einstein published the general theory of relativity. His central insight was radical. Gravity is not a force transmitted between masses. Instead, it is a manifestation of curvature in the fabric of space-time itself. That phrase, curvature of space-time, can sound like empty jargon, so let us unpack it methodically. Start with space and time as we ordinarily conceive them. Space is the three-dimensional arena in which objects exist. You can move forward and backward, side to side, up and down. Time seems different. It appears to flow in a single direction from past to future. You experience events sequentially and cannot reverse course. Space tells you where things happen. Time tells you when. They seem fundamentally distinct. Einstein showed they are not. Space and time are interwoven into a single four-dimensional continuum he called space-time. This is not merely a mathematical convenience. It reflects physical reality. You cannot have space without time or time without space. They are two aspects of one unified structure. Every event in the cosmos occurs at a specific location in this four-dimensional tapestry, not just at a place and at a moment separately, but at a point in space-time. Here is where things become extraordinary. Space-time is not rigid, it flexes, it warps. And what warps it is mass and energy. Any object possessing mass or energy distorts the space-time surrounding it. Greater mass means greater distortion. Earth warps the space-time in its vicinity. The Sun, being far more massive, warps it much more dramatically. Even your own body bends space-time, though by an amount so small it is utterly negligible. A popular way to visualize this is to imagine a taut rubber sheet. Place a heavy ball on it and the sheet sags. Roll a smaller ball nearby and it curves toward the heavy one, following the slope of the depression rather than traveling in a straight line. From the smaller ball's own perspective, it is simply following the most natural path available. But because the sheet is curved, that path bends toward the heavier ball. This analogy helps with intuition, but has real limitations. The rubber sheet is two-dimensional and deforms into a third dimension. Space-time is four-dimensional and its curvature is intrinsic, meaning the warping is a property of the fabric itself, rather than a bending into some higher dimensional container. Also, the rubber sheet picture uses gravity itself to make the heavy ball sag, which is circular when the goal is to explain gravity. So treat the image as a rough sketch rather than a literal description. What does intrinsic curvature actually mean? It means the rules of geometry change in flat space. The shortest distance between 2 points is a straight line. In curved space, straight lines in the classical sense do not exist. Instead, there are geodesics, the paths representing the shortest or most natural routes between 2 points within that curved geometry. On the surface of Earth, which is curved, the shortest route between two distant cities is not a ruler straight line on a flat map. It follows what is called a great circle. Airline routes from New York to Tokyo pass over Alaska, which looks bizarre on a flat projection, but is actually the most efficient path on a sphere. In curved space-time, objects follow geodesics. A planet circling the Sun is not being yanked by an invisible rope. It is tracing the most natural path through the warped space-time the Sun creates. From the planet's own frame of reference, it is moving in a straight line, but because space-time is curved, that straight line, viewed from outside, looks like an elliptical orbit. The planet is perpetually falling toward the Sun, yet moving sideways quickly enough that it continually misses, locked in an endless state of free fall. This reframes weightlessness in a striking way. Astronauts aboard the International Space Station float not because they have escaped Earth's pull. At their orbital altitude of roughly 400 kilometers, the gravitational field is still about 90% as strong as it is on the surface. They feel weightless because they are in free fall. The station and everyone inside it are following geodesics through curved space-time, all falling toward Earth together, all moving sideways fast enough to keep missing it. Relative to the station, the astronauts drift effortlessly. You taste the same phenomenon whenever you jump during the brief instant your feet leave the ground and you arc through the air. You are in free fall, genuinely weightless. The moment is so short you barely notice it, but if you could somehow remove the ground and keep falling, you would feel exactly what orbital astronauts feel. Imagine riding inside an elevator whose cable snaps. As it plummets, you float inside it, weightless, because you and the elevator are falling together. Now imagine floating inside that same elevator in deep space, far from any star or planet. You would also float. Einstein realized these two scenarios are indistinguishable from the inside. Free fall in a gravitational field and drifting through empty space produce identical experiences. This is the equivalence principle, one of the conceptual pillars supporting general relativity. The equivalence principle runs in both directions. Standing on the ground, you feel the floor pressing upward against the soles of your feet. That sensation is what you call weight. Now picture yourself inside a rocket in deep space, accelerating at 9.8 meters per second squared. The floor pushes up against you in exactly the same way. No experiment performed inside the rocket could distinguish between standing on Earth and accelerating through empty space at that rate. The two situations are physically equivalent. This leads to predictions that sound bizarre, yet are experimentally confirmed. One is gravitational time dilation. Time passes at different rates depending on your location within a gravitational field. Deeper in the field, where space-time is more severely curved, clocks tick more slowly. This is not a subjective illusion, it is an objective physical fact. Synchronize two clocks, leave one on a valley floor and carry the other to a mountain top. Then bring them back together. The valley clock will have accumulated less elapsed time. The difference is tiny under normal conditions, but real and measurable. In 1971, researchers placed highly accurate atomic clocks aboard commercial jets and flew them around the world. Upon landing, those airborne clocks were ahead of identical clocks that had remained on the ground by precisely the amount general relativity predicted. The discrepancy was measured in nanoseconds, but it was unambiguous. Today, the global positioning system depends on accounting for this effect. Atomic clocks on GPS satellites run slightly faster than ground clocks because they sit higher in Earth's gravitational well, where space-time is less curved. Without relativistic corrections, GPS position calculations would drift by kilometers within hours. Every time you navigate with a phone, you're relying on Einstein's predictions being correct. General relativity also predicts that light follows geodesics, just like everything else. When light passes near a massive body, its path bends. The massive body acts as a gravitational lens. This was first confirmed during a total solar eclipse in 1919, when astronomers photographed stars whose light grazed the sun. Those stars appeared slightly displaced from their catalogued positions, shifted by about 1.8 arc-seconds, precisely what Einstein had calculated. The result made front-page headlines worldwide and turned Einstein into a global celebrity almost overnight. Gravitational lensing is now a standard observational technique. When light from a remote galaxy passes through or near a massive foreground cluster, it can be bent into arcs, rings, or multiple copies of the same source. Studying these distorted images allows astronomers to map the distribution of mass within the lensing cluster, including dark matter, which emits no light but still warps space-time. Black holes represent the most extreme manifestation of space-time curvature. A black hole is a region in which space-time is bent so drastically that no trajectory, not even one followed by light, leads outward. The boundary marking this point of no return is the event horizon. Cross it and every possible geodesic carries you inward toward the center. Escape becomes not merely difficult, but geometrically impossible. Black holes arise when the most massive stars exhaust their nuclear fuel, Throughout a star's life, a balance holds between the inward crush of gravity and the outward push of energy released by fusion. When fuel runs out and fusion ceases, the outward pressure vanishes. For a star exceeding roughly 20 solar masses, the collapse proceeds without limit. All the stellar matter compresses into a singularity, a point of theoretically infinite density surrounded by the event horizon. The size of the event horizon scales with mass. For a black hole equal to the Sun in mass, the horizon radius would be about 3 kilometers. For one containing 1 billion solar masses, like those lurking at the hearts of large galaxies, the horizon stretches to nearly 3 billion kilometers, dwarfing the orbit of Saturn. That a single object can enclose such a volume challenges everyday intuition. From the viewpoint of someone falling into a black hole, the crossing of the event horizon happens in finite time. Depending on the black hole's mass, it might take seconds, minutes, or hours. But from the perspective of a distant observer, the infalling person never quite reaches the horizon. Gravitational time dilation grows without bound as the horizon is approached. Light from the falling person shifts to ever longer wavelengths, from visible to infrared to radio, growing dimmer and dimmer until the person appears frozen and fading just outside the boundary. This is a perspective effect. The person themselves notices nothing special at the horizon. Inside, however, space-time is so distorted that the singularity lies not in a direction you can steer away from, but in your future as unavoidable as tomorrow. At the singularity, the mathematics of general relativity produces infinities, which almost certainly signals that the theory has reached its limits. Most physicists suspect that quantum effects absent from general relativity become dominant before the true center is reached. A complete theory of quantum gravity would be needed to describe what actually happens there, and no such theory has been confirmed. The cosmic censorship conjecture, proposed by Roger Penrose, holds that all singularities are cloaked behind event horizons, hidden from external view. Naked singularities, ones visible from the outside, would represent points where deterministic physics breaks down in plain sight. Nature appears to forbid them, though. Why it does so remains an open question. Contrary to popular imagery, black holes are not cosmic vacuum cleaners indiscriminately devouring everything nearby. A black hole's gravitational influence at a given distance is identical to that of any other object of equal mass. Replace the Sun with a black hole of the same mass, and Earth's orbit would continue unchanged. The planet would freeze without sunlight, but it would not spiral inward. Trouble arises only when you venture very closer than you could ever approach a normal star, because the star's physical surface would be in the way. With a black hole, the matter has collapsed inside the horizon, allowing you to approach the center of mass much more closely. At short-range tidal forces, the difference in gravitational pull between your near side and far side become ferocious. Falling feet first, your feet would be pulled harder than your head. As you drew closer, the stretching would grow until you were pulled apart into a thin stream of matter, a process physicists whimsically call spaghettification. For a small black hole, this happens well outside the horizon. For a supermassive one, the horizon is so far from the center that tidal forces there are relatively mild. Destruction comes later, deeper inside. Black holes are not entirely black. In 1974, Stephen Hawking predicted that quantum effects near the event horizon cause black holes to emit faint thermal radiation, now called Hawking radiation. In the quantum vacuum, particle-antiparticle pairs constantly flicker into and out of existence. Near a horizon, one member of such a pair can fall in while the other escapes. The escaping particle carries energy away, so the black hole gradually loses mass and shrinks. For a black hole of stellar mass, the evaporation time scale is staggeringly long, around 10 to the 67th power years, incomprehensibly longer than the current age of the cosmos. Supermassive black holes would take even longer. But hypothetical tiny black holes, if any exist, could evaporate rapidly, exploding with the energy of many nuclear weapons in their final moments. None have been observed. Gravitational waves count among the most dramatic confirmations of Einstein's theory. Accelerating masses create ripples in the space-time fabric itself, disturbances that propagate outward at light speed. Picture dropping a stone into still water. Waves radiate across the surface. Gravitational waves are analogous, except the medium being disturbed is space-time. As such a wave passes through a region of space, it alternately stretches distances in one direction and compresses them in the perpendicular direction. Einstein predicted these waves in 1916, but doubted they could ever be detected, because the distortions they produce are absurdly small. Indirect evidence arrived in the 1970s when Russell Hulse and Joseph Taylor discovered a pair of neutron stars orbiting each other. The orbit was shrinking at exactly the rate expected if the system were radiating energy in the form of gravitational waves. That discovery earned a Nobel Prize in 1993. Direct detection required instruments of almost inconceivable sensitivity. The Laser Interferometer Gravitational Wave Observatory, or LIGO, consists of two facilities separated by 3,000 kilometers, one in Louisiana and one in Washington state. Each has two perpendicular arms 4 kilometers long through which laser beams bounce back and forth. A passing gravitational wave alters the relative lengths of the arms by a distance smaller than 1/10,000th, the diameter of a proton. Measuring such a change is like gauging the distance to a nearby star accurate to the width of a human hair. On September 14, 2015, both LIGO detectors registered a signal. Analysis revealed it originated from two black holes, one 29 and the other 36 times the mass of the Sun, spiraling together and merging 1.3 billion light-years away. The resulting black hole weighed 62 solar masses. The arithmetic shortfall of 3 solar masses was converted entirely into gravitational wave energy in accordance with the equivalence of mass and energy. During the final fraction of a second of that merger, the power output in gravitational waves exceeded the combined luminosity of every star in the observable universe by roughly a factor of 50. That number borders on incomprehensible. Since that landmark event, dozens more gravitational wave detections have followed. Most involve merging black holes, but some involve colliding neutron stars. In 2017, LIGO and its European partner, Virgo, detected waves from a neutron star merger that was simultaneously observed across the electromagnetic spectrum from gamma rays to radio. That event inaugurated multi-messenger astronomy, studying cosmic phenomena through multiple independent channels of information. Gravitational wave science is not limited to confirming that waves exist. The signals encode detailed information about the sources. Neutron star mergers carry imprints of the exotic matter inside these ultra-dense objects, matter compressed to densities where atomic nuclei merge into states unreproducible in any laboratory. Different theoretical models of how matter behaves under such conditions predict slightly different waveforms, so analyzing the signals amounts to probing the internal structure of neutron stars from across the cosmos. The observations also constrain fundamental physics. Gravitational waves travel at precisely light speed, a result that was not guaranteed and that rules out entire families of alternative gravity theories predicting a different speed. Gravitational waves additionally provide a novel yardstick for cosmic distances. The wave amplitude reveals how far away the source is, while the frequency evolution reveals the masses involved. If traditional telescopes can identify the host galaxy and measure its recession velocity, the combination yields an independent measurement of the universe's expansion rate. This technique may help resolve an ongoing tension between different methods of measuring that rate, each of which currently gives a slightly different answer. Planned future detectors will extend the reach of gravitational wave astronomy enormously. A space-based observatory called LISA, scheduled for the 2030s, will consist of 3 spacecraft forming a triangle with sides 5 million kilometers long. It will be sensitive to lower frequency waves generated by supermassive black hole mergers during galaxy collisions, events too slow for ground-based instruments but releasing staggering amounts of energy. 2 of the biggest enigmas in modern physics are dark matter and dark energy. When astronomers measure the orbital speeds of stars within galaxies, they find that stars in the outer regions move far faster than the visible mass alone can explain. The only viable explanation is additional unseen mass providing extra gravitational influence. This unseen component is called dark matter. It does not emit, absorb, or reflect any electromagnetic radiation, making it invisible to every kind of telescope, yet it possesses mass, and therefore curves space-time, shaping the motions of visible matter around it. Approximately 85% of all matter in the universe is dark. Only 15% is the ordinary kind that composes stars, planets, and living creatures. Despite decades of effort, no one knows what dark matter actually is. It is not merely dark clouds of normal material, because such clouds would block background light. Dark matter is utterly transparent. Leading hypotheses invoke undiscovered subatomic particles interacting with ordinary matter only through gravity. Underground detectors designed to catch rare collisions between dark matter particles and atomic nuclei have so far produced no conclusive signal. Dark energy is stranger still. In 1998, 2 teams studying distant supernovae independently discovered that the expansion of the universe is not slowing down under gravity's influence as everyone had assumed. It is accelerating. Something is driving space apart faster and faster. This mysterious agent, dubbed dark energy, appears to be an intrinsic property of empty space itself. As the universe expands and new space is created, more dark energy appears, further accelerating the expansion in a self-reinforcing cycle. Dark energy accounts for about 68% of the total energy content of the cosmos. Dark matter contributes around 27%. Ordinary matter makes up roughly 5%. 95% of the universe consists of substances we do not understand. That fact alone should inspire humility. The accelerating expansion has sobering implications for the distant future. Galaxies beyond our gravitationally bound neighborhood are receding ever faster. Eventually, their light will no longer be able to reach us. In trillions of years, the observable universe will have contracted to just the merged remnant of our local galaxy group. Civilizations arising in that remote epoch would see only their own galaxy surrounded by emptiness. They would have no observational evidence that the universe was ever larger, no way to deduce the Big Bang, no access to the cosmological knowledge we currently take for granted. We are fortunate to exist at a moment when the broader cosmos is still visible and studyable. General relativity is not merely a theory of gravity, it is a theory of the universe's structure and evolution. In 1922, Alexander Friedmann used Einstein's equations to show that the cosmos must be either expanding or contracting. A static universe is unstable. Einstein himself initially resisted this conclusion, preferring to believe in an eternal, unchanging cosmos. Then in 1929, Edwin Hubble observed that distant galaxies are receding from us, and the farther away a galaxy is, the faster it moves. The universe is expanding, space itself is stretching, carrying galaxies along. If the universe is growing now, it was smaller in the past. Trace the expansion backward and everything converges toward an unimaginably hot, dense state. This is the Big Bang, not an explosion occurring at some location within pre-existing space, but the expansion of space itself beginning from a near singular condition. Three independent lines of evidence support this picture overwhelmingly. First, galaxies are moving apart. Second, the cosmos is bathed in faint microwave radiation, the cosmic microwave background, which is the cooled afterglow of the epoch roughly 380,000 years after the initial expansion, when the universe became transparent to light. Third, the observed abundances of light elements, hydrogen, helium, and traces of lithium, match theoretical predictions for nuclear reactions occurring in the first few minutes of the universe's existence. The Big Bang framework places the origin of the universe approximately 13.8 billion years ago. Before that moment, there was no before in any physically meaningful sense, because time itself commenced with the expansion. Asking what preceded the Big Bang is akin to asking what lies north of the North Pole. The question rests on a concept that does not apply. Time is part of space-time. When space-time began, time began. The earliest fractions of a second after the Big Bang remained speculative because the temperatures and densities were so extreme that a theory of quantum gravity is needed to describe them. No such theory has been confirmed. From about 1 second onward, however, established physics applies, and its predictions match observations with impressive precision. Whether the universe is spatially finite or infinite remains unknown. The observable universe, the region from which light has had time to reach us, spans roughly 93 billion light-years in diameter. Beyond that boundary lies space we cannot yet see. Current measurements indicate that the universe is spatially flat on the largest scales, consistent with being infinite, but a very large yet finite cosmos curved back on itself like the surface of a higher dimensional sphere is also possible. We lack sufficient data to settle the question. Among the more exotic predictions of general relativity is frame dragging. A massive rotating body drags space-time around with it as it spins. For Earth, the effect is minuscule, but it has been measured. In 2004, NASA launched Gravity Probe B carrying 4 gyroscopes of extraordinary perfection, so spherical that if scaled to Earth's size, their highest bumps would rise only a couple of meters. Over more than a year in orbit, the satellite detected tiny shifts in gyroscope orientation caused by Earth's rotation dragging space-time, precisely matching Einstein's predictions. Frame dragging becomes far more dramatic near a spinning black hole. A rotating black hole drags space-time into a vortex around itself, creating an ergosphere, a region outside the event horizon where space-time swirls so forcefully that nothing can remain stationary. You would be compelled to co-rotate. In principle, energy can be extracted from a spinning black hole through a mechanism called the Penrose process, in which an object entering the ergosphere splits, so that one fragment falls inward, carrying negative energy, while the other escapes with more energy than the original object possessed. The black hole surrenders some of its rotational energy in the exchange. This is a legitimate consequence of the mathematics, though whether any civilization could engineer such a feat remains an open question. General relativity's equations also permit solutions containing closed time-like curves, trajectories through space-time that loop back to earlier times, theoretically enabling travel into the past. Such solutions appear in certain exotic space-time geometries. They raise the familiar paradoxes of time travel, such as preventing your own birth. Most physicists suspect that nature forbids these loops through mechanisms not yet fully understood, perhaps involving quantum effects that destabilize any region where such curves might form. The issue remains unresolved. Despite passing every experimental test thrown at it for over a century, general relativity is known to be incomplete. It is fundamentally incompatible with quantum mechanics. Quantum mechanics governs the subatomic realm and is inherently probabilistic. Particles do not possess definite properties until measured. They exist in superpositions of multiple states simultaneously. General relativity, by contrast, is deterministic. Given the curvature of space-time and the initial conditions, future trajectories can be computed with certainty. No probability, no uncertainty, no superposition. The two frameworks operate on clashing principles. For most situations, this incompatibility is irrelevant because the domains do not overlap. Quantum mechanics handles the small, general relativity handles the large, but in certain extreme environments both are essential. Inside a black hole, space-time curvature diverges while the region shrinks to subatomic dimensions. At the Big Bang's origin, the entire universe was smaller than an atom, yet space-time curvature was immense. Understanding these situations demands a theory unifying both frameworks. String theory attempts this by modeling fundamental particles not as dimensionless points, but as tiny vibrating filaments whose different vibration patterns correspond to different particles. Gravity emerges naturally in this framework as one particular vibrational mode. However, string theory requires extra spatial dimensions beyond the 3 we perceive, perhaps 10 or 11 in total, supposedly curled up too small to detect. Despite mathematical elegance, it has produced few testable predictions, and none have been confirmed or refuted. Loop quantum gravity takes a different path, proposing that space-time itself is granular at the smallest scales, composed of discrete loops rather than a smooth continuum. This discreteness would prevent the infinities that plague current theories at singularities. But this approach, too, struggles to generate predictions accessible to experiment. Other ideas abound, including theories in which gravity is an emergent phenomenon arising from deeper microscopic physics, or frameworks questioning whether space-time is fundamental at all. The correct theory of quantum gravity remains one of the greatest unsolved problems in science. Even without that final theory, general relativity has practical consequences that touch daily life. GPS navigation is the most familiar example, but the technologies developed for gravitational wave detection, ultra-stable lasers, vibration isolation systems, mirror coatings of extreme reflectivity, spin-off into telecommunications, precision measurement, and fundamental research. At every scale, gravity shapes the universe. On Earth, it holds the atmosphere, sorted primordial molten material by density to create core and crust, drives mantle convection and plate tectonics, builds mountains and carves ocean trenches. In the solar system, the sun's gravity orchestrates planetary orbits. Jupiter's gravitational influence sculpts the asteroid belt, creating gaps at orbital resonances where repeated tugs clear debris. Saturn's moons shepherd ring particles into intricate structures, comets drifting in the distant Oort cloud occasionally receive gravitational nudges from passing stars or galactic tides and plunge sunward, sometimes colliding spectacularly with planets as comet Shoemaker-Levy 9 did with Jupiter in 1994. Stars themselves are gravity's creations. Dense knots within vast molecular clouds collapse under self-gravity, heating until nuclear fusion ignites, establishing a balance between inward gravitational compression and outward radiative pressure that can persist for billions of years. When fuel is exhausted, gravity reasserts itself. Low-mass stars shed their outer layers and leave behind white dwarfs. Massive stars explode as supernovae, scattering heavy elements into space, elements later incorporated into new stars, planets, and living organisms. The carbon in your cells, the iron in your blood, the calcium in your bones, all were forged inside stellar furnaces or during supernova detonations and have traveled through the cosmos for billions of years before assembling into you. That is not poetic metaphor, it is literal fact. Neutron stars, remnants of supernova cores, pack roughly 1.4 solar masses into a sphere only 20 kilometers across. A teaspoon of neutron star material would weigh about 1 billion tons. Surface gravity is 200 billion times Earth's. Some neutron stars spin hundreds of times per second, emitting beams of radiation that sweep past Earth as regular pulses, earning them the name pulsars. When pulsars were first discovered in 1967, the signals were so precisely periodic that some researchers half-seriously considered the possibility of artificial origin before the natural explanation, rapidly spinning neutron stars, was confirmed. Galaxies are gravitationally bound assemblies of hundreds of billions of stars, along with gas, dust, and vast quantities of dark matter. The Milky Way spans roughly 100,000 light-years and contains somewhere between 200 billion and 400 billion stars, all orbiting the galactic center. Our Sun sits about 26,000 light-years from that center, completing one full orbit every 225 million years or so. The last time the Sun occupied this position in its galactic circuit, dinosaurs were just beginning to appear on Earth. Galaxies interact gravitationally. When two pass close, their mutual gravity distorts them, stretching spiral arms and flinging stars into long tidal streams. Sometimes they merge entirely. The Milky Way is currently absorbing a smaller companion, the Sagittarius dwarf galaxy, shredding it into stellar streams wrapped around our galaxy. In roughly 4 billion years, the Milky Way will collide with the Andromeda galaxy, which is approaching at about 110 kilometers per second. The merger will unfold over hundreds of millions of years. Individual stellar collisions will be rare because the space between stars is enormous, but gas clouds will compress, igniting dramatic bursts of star formation. Eventually, the two spirals will blend into a single large elliptical galaxy, harboring a central black hole of tens of millions of solar masses. On the largest observable scales, galaxies are not scattered randomly. They organize into a cosmic web of filaments, sheets, and nodes separated by immense voids. This architecture grew from minute density fluctuations in the early universe. Regions slightly denser than average exerted slightly stronger gravity, attracting more matter. Growing denser still, pulling in yet more. A self-amplifying process that over billions of years sculpted the grand filamentary structure mapped by modern galaxy surveys. Gravitational time dilation, far from being a theoretical curiosity, has been measured under remarkably ordinary conditions. In 2010, researchers at the National Institute of Standards and Technology demonstrated that two atomic clocks separated vertically by just 33 centimeters, barely more than a foot, showed measurable differences in elapsed time. The higher clock ran faster by about 90 trillionths of a second per day. General relativity predicted exactly that. Near extreme objects, the effect intensifies. On a neutron star's surface, time runs about 30% slower than far away. At a black hole's event horizon, time dilation becomes infinite from an external observer's standpoint. This connects to the black hole information paradox. Quantum mechanics insists that information can never be truly destroyed. The evolution of any quantum system is in principle reversible. Given complete knowledge of the current state, you can reconstruct any past state. But if matter-carrying information falls into a black hole, and the black hole eventually evaporates through Hawking radiation, what happens to that information? If it is lost, quantum mechanics is violated. If it is somehow preserved, how does it get out? Stephen Hawking originally argued that information genuinely vanishes, a stance that provoked fierce debate. He later reversed his position, suggesting that information might be encoded in subtle correlations within the Hawking radiation. Recent theoretical work invokes the holographic principle, proposing that all the information about a three-dimensional volume of space can be encoded on its two-dimensional boundary, much like a hologram. For a black hole, the event horizon serves as that boundary. Information about everything that fell in might be preserved in the horizon's quantum structure and gradually released as the black hole evaporates. Fully understanding this requires a working theory of quantum gravity, which we do not yet possess. The information paradox remains one of the deepest unresolved questions bridging gravity, quantum theory, and the fundamental nature of information. General relativity also imposes a universal speed limit. Nothing carrying information or mass can travel faster than light. This is not because light has some arbitrarily special velocity. Light travels along null geodesics, the boundary between paths accessible to massive objects and paths that would imply traveling backward in time. The speed of light is the speed of causality itself. As you accelerate an object toward that limit, the energy required climbs without bound. Reaching light speed would demand infinite energy, which is impossible. This has stark implications for interstellar travel. The nearest star system is over 4 light-years away. Even at a large fraction of light speed, journeys between stars would take years, and time dilation introduces a poignant asymmetry. A traveler moving at 99% of light speed to a star 10 light-years distant would experience only about 1.5 years of personal time each way, but more than 20 years would elapse on Earth. Return home and everyone you knew would have aged 2 decades while you aged 3 years. Push the speed higher and the disparity grows. At 99.9% of light speed, a journey spanning the galaxy, 100,000 light-years as measured externally, would feel like roughly 4,000 years to the traveler, while 100 millennia pass for the rest of the universe. These numbers are not speculation. They follow directly from well-tested mathematics and are confirmed daily in particle accelerators, where fast-moving particles live far longer than their stationary counterparts before decaying. The universe imposes a bittersweet trade. Travel fast enough, and you can, in principle, reach distant destinations within a human lifetime as measured by your own clock. But the civilization you left behind will have aged centuries or millennia. You become an exile in time, severed from your origin not just by distance, but by the relentless geometry of space-time. The ultimate fate of the cosmos depends on the interplay between gravity and dark energy. Because the expansion is accelerating, distant galaxies will eventually recede beyond our observational horizon. In the very far future, trillions upon trillions of years hence, all stars will have exhausted their fuel. White dwarfs will cool into inert black dwarfs. Neutron stars will persist as cold remnants. Black holes will slowly evaporate through Hawking radiation over timescales dwarfing anything imaginable. Eventually, even the black holes will be gone, leaving only a dilute sea of elementary particles and low-energy photons drifting through ever-expanding darkness. This is the heat death, the ultimate thermodynamic equilibrium of a cosmos that has spent all its usable energy, but that endpoint lies so far in the future as to be almost meaningless on any human timescale. For now, the universe teems with activity. Stars igniting, galaxies colliding, black holes growing, gravitational waves rippling across billions of light-years, and on at least one small rocky world, a species struggling to comprehend it all. What should you carry away from all of this? Gravity is not a force tugging you downward. It is the geometry of space-time curved by mass and energy. Objects follow geodesics through that curved geometry. What you call weight is the sensation of the ground's electromagnetic forces preventing you from following your natural geodesic toward Earth's center. In freefall, you feel weightless not because gravity has vanished, but because you are finally free to follow that natural path. Space and time are not separate stages. They are a single dynamic fabric that flexes in response to the matter and energy it contains. That flexing dictates how objects move, and the moving objects flex the fabric in return, a continuous feedback loop giving rise to every gravitational phenomenon, from falling raindrops to the large-scale expansion of the cosmos. General relativity has been validated by every observation and experiment devised to test it. The anomalous precession of Mercury, the bending of starlight near the Sun, the slowing of clocks in stronger gravitational fields, the orbital decay of binary pulsars, the direct detection of gravitational waves, and the imaging of black hole shadows. It is among the most thoroughly confirmed theories in the history of science. Yet it is incomplete. It does not incorporate quantum mechanics. We still lack a theory of quantum gravity. Dark matter and dark energy, together constituting 95% of the universe's content, remain unexplained. We do not know whether the cosmos is finite or infinite, whether other universes exist, or what truly happens at the center of a black hole. These open frontiers are not failures. They are invitations. Every unanswered question is a doorway to deeper understanding. Future gravitational wave observatories will detect signals from sources invisible to any telescope. Observations of black hole photon rings will test general relativity with unprecedented precision. Experiments probing whether gravity influences quantum superpositions may reveal where classical spacetime gives way to something more fundamental. Searches for primordial gravitational waves imprinted on the cosmic microwave background could confirm or refute inflationary cosmology and expose physics at energy scales trillions of times beyond the reach of any particle accelerator. There is something quietly profound about recognizing that you are not standing still on a static platform with an invisible force pressing you down. You are accelerating through curved space-time, held in place by electromagnetic interactions between the atoms in your shoes and the atoms in the floor. Remove the floor and you would follow your geodesic freely, weightless, tracing the natural contours of the cosmos. Out beyond this planet, moons orbit worlds, worlds orbit stars, stars orbit galactic centers, and galaxies stream along the curved architecture of cosmic space-time. Light from ancient sources has been traveling for billions of years through expanding space to reach your eyes. Gravitational waves from cataclysmic collisions ripple silently through the fabric of reality at this very moment, stretching and compressing space as they pass through you unnoticed. We are small creatures on a modest planet orbiting an ordinary star in one galaxy among hundreds of billions, yet we have decoded the fundamental principles governing the structure and evolution of the cosmos. We have measured space-time curvature, detected ripples from colliding black holes over 1 billion light-years distant, photographed the shadows of supermassive black holes, and reconstructed the history of the universe back to fractions of a second after its origin. The fact that reality is comprehensible at all is itself astonishing. The laws of physics appear to be the same everywhere and at every time, accessible to patient observation, creative experimentation, and disciplined reasoning that should inspire confidence. The universe is knowable. We have known a great deal already. We will know more. And every person who pauses to wonder how gravity works, what space-time means, or why the night sky looks the way it does, is participating in that ancient and ongoing endeavor to understand where and what we are. You're not being pulled downward by a mysterious force. You are navigating the geometry of a four-dimensional cosmos, riding the curvature of space-time shaped by every mass and every quantum of energy in the universe.